So in this problem, we have a bunch of resistors arranged in an unusual circuit. Before we can figure out the current flowing for any of these resistors, we have to figure out the total resistance of the circuit. So to do that, if we take a look at this, we've got, and if we start in the sort of inside, we have these two resistors in series. So these two together, since in series, is just 12 ohms. I'm going to leave off the symbol. That is then in parallel with this resistor, which is 6 ohms. 1 over 12 plus 1 over 6, the reciprocal of that, means that these are going to be 4 ohms. That's in series with this 8. I'm going to work my way around this way, which means this again is 12 ohms. And then that is in parallel with this 6 ohms, which again reminds us 12 and 6 in parallel is going to give us 4 ohms again. And at this point, I'm going to stop because there's way too many lines. This now is in series with this one, giving us 8 ohms. This whole 8 ohms is in parallel with this 8 ohms, means that's 4 ohms. All of this 4 ohms is now in series with this, which gives us 8 ohms again. That 8 ohms is in parallel with this 8 ohms, which gives us 4 ohms. So this whole thing over here is 4 ohms. It's in series with this 6. The total resistance of this network is 10 ohms, which means our current flowing out of the battery, just using V over R, it's a 20-volt battery. The resistance is 10, gives us, of course, 2 amps. And once we get that, we can start solving the rest of this. So I'm going to skip here and go to this at this point and start talking about the voltage drops across the circuit. We know there's 2 amps flowing through this one. And at this point, we've got it branches. Part of the current's going to go this way. Part of the current's going to go this way. And if you remember, this whole section of the circuit is 8 ohms. And this is 8 ohms. So you can probably very quickly guess this is going to be 1 amp and 1 amp. When it comes down to over here, again, this is a little bit hard to remember. This point junction here is a little painful because it's going to split up 1, 2, 3, 4 ways. That's a little bit more challenging. So I'd recommend at this point we start looking at the voltage drops. We start at 20 volts over here. I'm going to make this 0 volts down here. We have a voltage drop of 12 up here, which means by this point we're at 8 volts. At this point down here, we're still at 0 volts because that's just a wire connecting those 2 points. Over here, we have voltage drop of 4, which means this point right here is 4 volts. And now we can actually calculate the current through that through this 8 ohm resistor. This has to be 1/2, just looking at the voltage drops. And the moment we know this is 1/2, look at the junctions coming out of here. We know there's 2 amps flowing back to the battery. We've got 1 amp coming down this bridge, 1 amp or half an amp coming this way, which means the current through this has got to be a half of an amp as well, which means the voltage drop across that is 2 volts, which means at this point in the circuit, we're at 2 volts, or we have to be at 2 volts, so we come back to 0 there. The moment we know that, we can start calculating some other currents. We know the voltage drop across this is 2. And so you can very quickly calculate the current on this one going down. 2 volts, it's going to be 1/3 of an amp. And believe it or not, we can start solving some other things as well. We had 1 amp coming in here. At this junction here, we've got 1/3 coming in, 1/2 coming out. We can actually calculate the current through this resistor right here. 2/6, this should be 1/6 of an amp, if I'm doing my math right. 1/6 plus 1/3 should equal 1/2. Let me just double check my math on that before I go any further. 1 divided by 3 plus 1 divided by 6 is 1/2. Okay, good. Which means we can calculate the voltage drop across this. 8 divided by 6 is 1.33. which means the voltage over here, and now, sorry, this is rather ugly. I'm going to put it as a decimal. Oh, maybe not. It has to be 2/3 of a volt. So that the voltage drop across this works. Once we have that, we can actually calculate the current now through this resistor right here. And that's the last piece of the puzzle, because once we get that, we can solve this one up here. Voltage drop across there, 4 minus 2/3, 10/3, and that's got to equal 6 times I. Ugh. Okay, so the current through this one, I'm going to leave it as a horrible fraction, has to be 5/9 of an amp. And you could write that as a something else. I'm actually curious about that. What is that? Ooh, 0.555. Okay, yeah, that makes sense. And now we can actually figure out the remaining current. We know the current coming into this junction is 1. We've got 1/2 going down this way, 1/3 going down this way, 5/9 going down this way. If I just do a little bit of math, 1 minus 1/2 minus 1/3 minus 5/9 tells us our remaining current is 7/18 of an amp. And that's also going to be going through this resistor here. There's no other path. My apologies for the really hideous numbers there. So what's the voltage drop across that top one? The voltage up here, and I'm going to leave it as a fraction again, is going to be 1/9 of a volt. Oh, that's the voltage drop. No, wait. Make sure I did that right. Hold on just a second. Voltage drop 35/9 plus 4 gives us 1/9. Okay. Yeah, I think it's right. Let me just double check my numbers. I messed up somewhere. Something doesn't quite feel right. The current through this top one should be, I'm going to put it as a decimal because I'm running out of, I can't quite figure out why it's not working. Should be 0.277 if you do the voltage drops. And then the voltage up at the top here, just as a decimal, should be, let's see, quick calculation, 1.22 volts. Forgive me for the decimals, which means we can now answer most of this. What's the current flowing through R6? That's going to be 1/3 of an amp. What's the voltage drop across R8? Voltage drop, just the current times that, should be a voltage drop of 2.77 volts. Yeah, double check my math one more time. It's still bothering me, but I'm fairly certain this is right. And now imagine that you took out the battery and replaced it with a charge inductor, which means the voltage, or it's already at whatever current it had in it. Um, how much time would it take this inductor to discharge to 95% of its stored current? To do that, we're just going to use this one. We know it's oops. Yeah, it should be decaying. Hold on, I'm just going to rewrite it. This is for increasing. This is for the decay. We're just going to use this one, and it actually doesn't matter. E to the negative RT over L. And solving this one is kind of nice. We want to know when it's down to discharge 95%. It's when the current is now 5% of what it originally started. So you're just going to plug in, oh, sorry, this is I0, is going to equal I0 times E to the negative 10, which is the total resistance of our circuit, times T over the inductance, which is going to be 0.65. We have to convert millihenries into henries. And from here, notice that I0 cancels out. And you just can take the natural log of 0.05 is going to equal negative 10t over 0.65. And you can take it from there, but just doing the math, give me just a moment to get my calculator warmed up. Natural log of 0.05, take that times 0.65, divided by 10, and the time required should be about 0.195 seconds. Yeah, this one is actually particularly ugly. You're right. Good luck with this one. Hope this helps. Oh, by the way, just real quick, that should be final. Yeah, this one's actually kind of interesting. Talk to you.